Pleasure to introduce the second speaker of this section, Professor Pedro Isaza, from the Universidade Nacional de Colômbia, sede Medellín. And the title of his talk is on the unique continuation of solutions to the Ostrovsky equation with negative dispersion.
Okay, thank you. First of all, I would like to thank the organizers, Felipe and Hermano, for inviting me to be in this conference. What I'm going to talk about is part of a work I have been doing lately with my colleagues, Eddie Bustamante and Jorge Mejia. I am going to be considering the Ostrovsky equation, which is this nonlinear dispersive equation. Here, the unknown function u is a function of the variable x and the time variable t. So this is a one-dimensional model. We have two signs here related to the dispersion. I'm going to be considering the equation with the minus sign. This is a perturbation of the well-known Korteweg-de-Vries equation with this non-local term that I will be calling dx minus 1, which is a certain antiderivative of the function f defined through the Fourier transform as division by IC. It's very easy to see that if function is in L2 and has dx minus 1 also in L2, then its mean value in the generalized sense is 0, and also that the dx minus 1 can be expressed just as the normal indefinite integral. We are going to prove a result that says, roughly speaking, that if the difference of two sufficiently smooth solutions decays for positive x as e to the minus x to the 8/5 at two different times, then both solutions are equal. We will follow the lines of the work of Koenig, Ponce, and Vega, all of them present here, and also their work joined with Skauriasa for the KdV equation. They basically, in 2002, considered a solution of the KdV equation, which vanishes for x larger than 0 at two different times, and proved that this solution must be identically 0 after applying some Karleman type estimates and a result due to Sott and Scheurer, which says that if a solution vanishes in an open set, then essentially it vanishes everywhere. Afterwards, in 2007, Skauriasa with Koenig, Ponce, and Vega considered the problem a little bit more relaxed of considering the difference of two solutions, not vanishing but decaying sufficiently fast at the rate of e to the x to the 3/2 for the positive values of x at two different times, proving that both solutions must be equal. This problem was considered by us for the Ostrovsky equation with positive dispersion, and I'm also going to consider it for the equation with negative dispersion, just after saying that we follow the lines of Koenig, Ponce, and Vega, but we have introduced notorious simplifications on their method, just keeping it so simple that we only use basically the definition of the Fourier transform, and we don't have to use sophisticated tools, more sophisticated tools of harmonic analysis like Lirelud-Palais decompositions, or the use of the theorem of the L2 boundedness of the maximal function associated to the inverse Fourier transform proved by Koenig and Thomas. Our theorem says that if we have two solutions of the equation, we require them to be continuous to H4, C1 to L2, and we impose some polynomial decay on the solutions for technical reasons. And the result says that if the difference of both solutions at t equal to 0 and 1 belong to, well, here I made a mistake, it's L2 of e to the ax to the 8/5. For all a larger than 0, then both solutions must be equal. Here x plus is just the positive part of the number x. This exponent perhaps is not the optimal one because in general, these exponents are related to the decay of the fundamental solution. So it is known that for the negative dispersion Ostrowski equation, this decay is of the same order of the one of the KdV equation. So perhaps this result is not optimal, but it is true. This theorem is proved by a mixture of some Karleman type estimates with an estimate that we call lower estimate. Since Karleman estimates are estimates done in exponentially weighted spaces, it's very important to set up the problem in these exponential weighted spaces by showing that if a solution or if two solutions of the Ostrowski equation with negative dispersion at t equal to 0 decay, if the difference has this exponential decay, then this decay is preserved for all times between 0 and 1, and with also for the derivatives up to order 3. The fact that this is preserved for the derivatives up to order 3 just comes from the fact that the solutions are in H4, and then we can apply an interpolation argument that produces the exponential decay, perhaps not with the same beta, but with a sufficiently good beta. This is proved in a very straightforward manner, just by taking like a function which flattened the exponential, and then making a priori estimates. We find that the derivative of v squared times this flattened exponential plus two positive terms are controlled by essentially the same integral of v squared. Here, for the equation with negative dispersion, we have the same sign of this positive term and of this positive term. In the equation with the positive dispersion, we have like a fight between these two signs, and then one cannot prove easily that the exponential decay is preserved. But here there is no problem, and then with this we can just easily apply Gronwall's lemma to obtain our conclusion. So we go to the Karleman estimates, which are essentially inverse properties of the linear operator associated to the equation. And I will abbreviate by D the band of all the reals in cross product with the interval 0, 1 of the time. So I will be calling D this band. So the Karleman estimate that we prove just is the following. We take a function with sufficient regularity, with a compact support in the space variable, having mean value 0. The mean value 0 is just to guarantee that the dx minus 1 operator is well defined, and prove that these norms of W and derivatives of order 1 and 2 in this exponential setting are bounded by this last term, which is related to the, or which is the norm of the linear part of the operator with weight e to the lambda x in some LP, LQ spaces, and also two terms that come from the boundary values of the function w at 0 and at 1. To prove a result like this, we produced a very easy and simple proof by considering the following. First of all, one reformulates the estimate just by calling this, we call this f, and then we reformulate it in such a way that what we have to prove is an inequality like this in terms of f. Since these functions are defined only in the band, we pass to the open space problem to use Fourier transform, and then suppose that f is a function defined in the open space. Then applying Fourier transform to this side, we call this part h, and then we have applied here Fourier transform. And then we can write each of the terms on the left-hand side of this expression. Each one of these three terms, we can write them as the function h, the Fourier transform, times a multiplier. This multiplier, I call it mk, m0, m1, and m2. I'm going to consider, for example, only m1. After normalizing a bit this, we obtain this expression with a polynomial of 4th order in the denominator, which is very easy to see that it only has simple roots. So it admits a factorization in 4 terms, and each one of the terms of the factorization gives rise to a partial fractional decomposition, where each one of the numerators can be computed by using the L'Hopital's rule to obtain explicitly that each one of the coefficients is given by this expression in terms of the roots of the polynomial. So it's easy to see also that for large values of tau, these roots, the cube of the roots times form are very apart from 1. So the denominator is bounded below, and then you produce a boundedness of the coefficients. And this allows to just to take the inverse Fourier transform of these expressions, first in terms of the variable tau, to see that this gives a bounded multiplier, which by use of elementary properties of convolution gives an estimate like this, Of course, these are estimates only made for open space. So we complete the proof just by considering a spatial function f, where we have taken the function w and multiplied it by a bound function of the time. And next to the boundaries, the derivatives of this function are approximations of the Dirac deltas. And in the inside, they behave well. So this application, when you make lambda epsilon tend to 0, give this part of the boundary part coming from these Dirac deltas that I have mentioned, and the other part. Okay, so what is the use of this Karleman estimate? So the idea is the following. When I consider the band, and I move sufficiently to the right, and I consider a band like this, and then very far from this point, I take another band. So since the estimate is given with a norm that includes all the band D, I just can't consider the left-hand side in a very smaller set, which is this set, but very far from to the right. And since this is multiplied by an exponential, I obtain something like a large exponential times some type of Sobolev norm bounded by something which is defined only on the left rectangle. So when I make R very large, this term goes very large. So this obliges this one to become small. So the other part that we need to do is just to take this that is obliged to be small and to bound it below to obtain something which is that the solution either is zero or we get a contradiction. So in this, we pass to the lower estimates, which say, roughly speaking, that if I take the difference of two solutions of the equation, we can bound this part below by considering then the two solutions. I take a rectangle placed at the origin. We see that if the difference V has an L2 norm which is larger than zero, then an inequality like this takes place with this exponential over here. This exponential is small, but still is a positive number. So to prove that, we consider a technical lemma which follows the ideas of the work of Koenig, Ponce, and Vega, which in turn used some ideas of Isakov. We consider a function phi like this, from 0 to 1, and then normalizing the x with a value of r large, and considering the function x over r plus phi of t, all this function here, we see that a level set of this function is something like a curve like this. Then we take a function g, vanishing at the borders, and having support contained in a set, the one that I am pointing out, where this is between 1 and 5. And then with that, we can prove an inequality like this. This is also a weighted inequality similar to the Karleman estimate, somewhat similar. Well, this is a technical proof where we consider the right part. We call the right part an operator T. We decompose it into three parts: a symmetric operator and an anti-symmetric operator, which are the same ones that are considered for the KdV equation, and also a remaining operator which comes from the dx minus 1. Computing using integration by parts, we can manage to prove that this TF, which is the right-hand side, this right-hand side, is bounded below by a positive thing, also a positive thing, which is the norm of f squared, and something which has undefined sign. Of course, we see that we can apply here the Cauchy-Schwarz inequality to obtain a norm of f here and a norm of L of f. So what we can observe is that we can compute this L of f and show that in this weighted setting, this is a bounded operator in L2 with the bounded with the exponential weights. So we perform a computation of this operator, apply Cauchy-Schwarz, make some sort of change of variable, and end up having that the norm of LF squared is bounded by the norm of f times r squared over alpha. So plugging in this in this expression, we can manage to have a negative term here that can be absorbed with the second one. Just if we take alpha and r in an adequate way, This is, if we take alpha larger than a constant times r to the 8/5 for sufficiently large constant c, then we can absorb this term with this term, just obtaining that the operator TF is bounded by a part coming from the norm of the first derivative and a part coming from the norm of the function itself. Then the rest of the proof is just to apply this lemma to a nice combination of cutting functions and so on, and obtaining that in this rectangle, one can bound the norm of the difference of the solutions with something which is given in this rectangle. Then the only thing that needs to be done afterwards is just to confront these two estimates to obtain that the solution has to be 0 in this rectangle. This really implies that the solution is 0 because we, by contradiction, suppose that the solution is not 0. Then there is a rectangle where the solution is not 0. If this rectangle is not at the origin, then you translate it to the origin and so on. And then we obtain the result saying that the difference of the solutions of the Ostrowski equation have to be 0. These are some references, the articles from Scauriaza, Kenny Poncian Vega, the original article of Ostrowski, and also the original article of Professor Sott and Scheurer. This is all what I had to say. Thank you for your attention.